Hi, this is Paolo Ferro who's speaking, and in my talk I would like to summarize the research work titled Residual Notch Stress Intensity Factor Assessment via 3D welding numerical simulation, influence of power input by myself, Professor Tang and Professor Berto. I will start with an introduction focusing on the goal of the work, and then I will proceed with the details of the numerical model, the result and discussion, and finally the conclusions. It is well known that the fatigue strength of welded joints depends on local stress field that arises at the weld toe or weld root. Because of such geometrical discontinuities, the local stress fields are singular in their nature, and this is the same thing when we are dealing with residual stress as well. Now, the residual stress influences the crack initiation in the high cycle fatigue regime where plastic effects can be neglected. For this reason, it is very important to assess the parameter that quantify the intensity of the singular residual stress field that is called residual notch stress intensity factor, in particular using 3D numerical models and therefore capturing boundary effects. Since 3D numerical models are tremendously demanding in terms of computational costs, numerical strategies are required to reduce the computational effort, such as the peak stress method. In this scenario, the influence of process parameters on the residual asymptotic stress distribution is not yet investigated using a 3D numerical modeling of the welding process. Therefore, this work is aimed at filling this gap. Computational welding mechanics and the peak stress method are combined to calculate the residual notch stress intensity factor as a function of the power input. Results are then summarized in terms of heat input and discussed in view of a future guideline proposal addressed to designers who are going to face a welding process optimization for fatigue life improvement. A butt welding process was simulated using Residual code with the methodology known as computational welding mechanics. Thermometallurgical and mechanical analysis were uncoupled. Moreover, the welding is supposed to be performed with only one pass. Taking advantages of the symmetry, only one half of the joint was modeled as shown in this figure, where the global Cartesian and local cylindrical reference systems are displayed as well. 33,110 8-note brick elements were used to build the mesh, the smallest ones in the vicinity of the weld toe having a size of 1 millimeter. It is shown that the weld toe profile is assumed to be a sharp V-notch with an opening angle of 135 degrees and a null tip radius that is the worst case condition. The material investigated in this work is the S355 structural steel, whose solid-state transformations are modeled using the Leblanc-Duval model when considering diffusional transformations, and Koinster-Marburger model when dealing with displacive transformation, as it is the martensitic transformation. Model parameters, of course, are calibrated by referring to the experimental CCT curves of the steel, as shown in this right side of this slide. The heat generation due to the heat source moving over the weld line is described by the power distribution function proposed by Goldak in 1984 for arc welding processes. Gaussian parameters of the Goldak heat source were chosen in a way that they produce a proper molten weld pool, radiative and convective heat loss was modeled using the Stefan-Boltzmann law and a convective heat transfer coefficients respectively. Sequentially, thermometallurgical mechanical uncoupled simulation was carried out where a dedicated function was employed to set the mechanical properties of the material to 0 in all nodes where the temperature, the computed temperature, was higher than the melting point. Moreover, isostatic clamping conditions were applied during and after welding. These two tables show on the left side the parameters of the heat source kept constant, and on the right side the power input values used in the trials. In local approaches, the weld toe is schematized referring to the worst case as a sharp V-notch zero-tip radius inducing an asymptotic stress field whose intensity is quantified by the notch stress intensity factor K' or K1, given by Gross and Mendelssohn definition in 1972 and described by equation 1 in this slide. When considering residual stresses, the notch stress intensity factor is called residual notch stress intensity factor, and a rapid technique used to calculate even by means of 3D numerical models is the peak stress method. It allows for estimation of the notch stress intensity factor and the residual notch stress intensity factor starting from the opening peak stress calculated at the V-notch tip with a coarse mesh, according to equation 2 in this slide, where in particular D is the average element size adopted to mesh the weld toe, and in this work D is equal to 1 millimeter. This figure shows the fusion zone produced by the heat source during welding as a function of power input. It is important to observe that the bit geometry was adopted according to the analyzed process parameters. The higher the heat input, the larger the weld bead. As a matter of fact, the bit geometry varies with process parameters, so that it was necessary to modify manually the geometry of the fusion zone, since fluid dynamic phenomena are not simulated in computational welding mechanics approach. Regarding the S355 steel microstructure, it is observed in the present figure that the weld bead is characterized by a mixture of bainite and ferrite, with an increase of ferrite as the power input increases. This is due to a decrease of a cooling rate with the increase of power inputs. Moreover, a stationary distribution of the microstructure is observed along the central part of the joint. This figure shows the residual notch stress intensity factor distribution along the entire weld toe and induced by the welding trial number 1. It is observed how the residual notch stress intensity factor distribution is characterized by high variation near the boundaries and a plateau far from them. Such stationary value is the same that is captured by 2D models, as demonstrated in a recent work published by the same author of this work. The 3D modeling highlights, therefore, the boundaries effects that seem more dangerous in terms of high values of residual notch stress intensity factors compared to the stationary residual notch stress intensity factor distribution. Different boundaries effects are observed at the source input zone compared to those that arose in the heat source output zone, reflecting the non-symmetric microstructure proportion at the boundaries induced by welding. This plot shows the residual notch stress intensity factor value calculated at the middle section of the specimen as a function of the heat input. It is interesting to note that an unexpected non-monotonic trend was found that can be justified by a strong interaction between geometry, weld bit size variation, and thermometallurgical history the joint undergoes for each different welding process combination. This interaction, here only captured by numerical simulation, will be surely a matter of future and interesting research work. So, we came to the conclusions. The residual notch stress intensity factor as a function of a power input was assessed via numerical simulation. Solid state phase transformation as well as weld bit geometry variation were considered. The obtained result showed a stationary value of the residual notch stress intensity factor in the middle zone of the bit, which reflects a stationary thermometallurgical history the joint undergoes. Boundary effects were captured as well that seems more dangerous than the stationary field characterized zone. Finally, a non-monotonic trend was captured between the heat input and the residual notch stress intensity factor value that is the result of a strong interaction between the geometry and the thermometallurgical history, and that merits to be further investigated in the next research work. Thank you very much for your attention. Here you can find my contacts in the case you are interested in my research topic and you need further details. Thank you again. Bye bye.